Welcome to the lecture part 3 of machine independent optimizations. In the last lecture we discussed induction variable elimination, strength reduction, etc. We also saw some parts of region based data flow analysis. Today we will continue with region based data flow analysis and then move on to the theory of data flow analysis. So, again very quick revision. So, we discussed regions which are groups of nodes, all edges between the nodes in N are in the region except for some of the back edges which enter the header, and the region may have multiple exits. So, the basic idea in region based analysis is to compute gen and kill for basic blocks in a certain region, gen r comma b and kill r comma b. So, in this we consider the definitions generated and killed along paths within the region or from the header of the region to the basic block B. Now, central to region based analysis is the computation of a transfer function called trans r comma b s. So, this tells us how the set S of definitions or anything else are modified when we pass through various regions. So, trans r comma b s is defined as gen r comma b union s minus kill r comma b, and if the input to this trans function is phi, then we get gen u comma b, which is nothing but out b. So, we basically want to compute gen u comma b, where u is the region containing the entire flow graph. Now, how do we get regions? We apply T1 T2 analysis, the transformations, and as we go on, every time we apply some transformation we get a bigger region. So, there is a hierarchy of regions which is built once we start applying the transformations to the time when we end applying the transformations. So, here is a very simple example. So, this is a flow graph. So, we apply a T1 transformation on C and D, again T1 transformation, T2 transformation on C and D, T2 transformation on A and B, T1 transformation on the region R containing C and D, this self loop is removed, and then we apply T2 transformation between these two regions T and S, and finally we apply the T1 transformation to remove this self loop, and we get the region V. So, when you look at the reaching definitions and see how region building happens in by T2 transformation and how gen r comma b gets computed, we have two situations. One is for T2 and the other is for T1. So, in the T2 transformation there is a region R1, another region R2, and we make a bigger region R. So, we are given the information about R1 and R2, and we want to compute the information about R. So, for basic blocks B within the region R1 there is no modification because it is not affected by anything in R2. There are no arcs going back from R2 to R1 within the region R. So, gen of R comma B and kill of R comma B remain the same as gen of R1 comma B and gen of kill of R1 comma B. But for R2 there are inputs coming from R1, and where in R1 do they come from? They are actually if you take this particular arc, it is a number of arcs connecting to various basic blocks in R1, and those are the basic blocks from which input can arrive into R2. So, for this reason we define G as union of gen of R1 comma P, where the P is all the predecessors P of the header of R2 in R1 are considered. Similarly, K is intersection of kill of R1 comma P with the same definition, and now gen of R comma B for basic blocks in R2 or gen of R2 comma B union G minus kill of R2 comma B. So, taking into account all those informations which are coming from R1. So, and then we presented the T1 transformation. This is very similar. So, here the kill does not get modified at all when we go from region R1 to R, simply because we would have considered all the acyclic paths in R1 to the header of B in computing kill. So, the kill information remains the same, kill of R comma B is kill of R1 comma B, but the gen information is computed in a way similar to that of T2 transformation. So, we consider G, which is the union of gen of R1 comma P. So, P is the set of all predecessors of R1 in R. So, you take the header of R1 and then all the predecessors, that gives you the set of predecessors. So, this is what we did for reaching definitions. Then we saw how exactly it can be computed for this example. So, for each step, when we built a region R, we said how to compute the gen and R sets. Then we applied a T1 transformation to build S. Again we said how to compute gen and kill. Then the same for T, then for U, and finally for building region U, and then finally for the region V. So, now we still have not seen what happens to this analysis when we compare it to the iterative data flow analysis. So, these are our well known equations of iterative data flow analysis for reaching definitions: out B equal to gen B union in B minus kill B, and in B equal to union of out P, where P is a predecessor of B, and in B equal to phi as a matter of initialization. So, if we go through the out and in computation, in about 4 iterations the set converges and does not change thereafter, and here are the out values which we get finally, and this is what we get by region analysis, and you can see that they are identical. So, whether we follow the region based analysis or we follow iterative data flow analysis, the answers will be the sets will be very similar, not much difference between these two. Now, what happens if we want to tackle the available expressions problem? So, if you recall the available expressions problem and the iterative solution that we gave, we had this as a forward data flow analysis problem, and we use the confluence operator as intersection. So, here something similar happens. The picture seems to be exactly the same as the previous case. Yes, it is indeed so. It is just that for basic blocks within R1 there is absolutely no change as before, but for R2 there are some changes. Here the gen and kill equations are identical, gen of R2 comma B union G minus kill of R2 comma B, and kill of R comma B is kill of R2 comma B union K minus gen of R2 comma B. So, in other words, whatever is generated within R2, that is taken, and then whatever is coming from R1 is taken, and then whatever is killed by R2 is removed from that. So, that is exactly what we used to do before. So, that is what we do here as well, but the computation of G is slightly different, and similarly K is also different. So, available expressions, we wanted the expression to reach on all paths. So, justifiably this G is intersection of gen of R1 comma P. For the reaching definitions, any one path was okay, but here we need the expression along all paths. So, it is an intersection. K is a union instead of the intersection, because if the expression is killed along any path, then it is completely killed. So, the G actually computation involves an intersection and K computation involves union. Similarly, in the case of T1 transformation, the gen part remains as gen of R1 comma B, there is no change, whereas the kill changes. The reason is for gen we would have already considered all paths in the region R1, An expression gets generated going from the header to B if and only if it is generated along all acyclic paths, and hence back edges incorporated into R will not cause any more expressions to be generated. So, we need not consider this back edge when we compute the gen sets. So, gen of R1 R comma B is same as gen of R1 comma B, but in the previous reaching definitions example this was not so, whereas kill of R comma B was the same as kill of R1 comma B, but and here it is different, kill of R1 comma B union k minus gen of R1 comma B. So, looks like the gen and kill equations are kind of interchanged from the reaching definitions problem to the available expressions problem. And like in the previous case, when we look at the available expressions problem in the iterative domain, we have the same kind of equations as before, and the confluence operator here is intersection, and the in B is U, the universe of all expressions. So, the value of again it converges in about 4 iterations. The final values are here, and the final values we obtain by region based analysis are here, and you can see that they are identical. So, whether we follow region based analysis or iterative analysis, the answer probably will always be the same, except of course, when there is a little bit of node splitting and so on, which we will see very soon. Then why do we want to apply region based analysis? In general, region based analysis is slightly faster than iterative analysis, but otherwise there is no huge advantage. So, how do we handle irreducible flow graphs? At some point of reduction in T1 T2 analysis, no further reduction is possible if the graph is irreducible, you will get stuck. At this point we split nodes, we have seen examples of this already. Regions are all nodes in this case, and duplicate them as explained earlier. So, we saw how node splitting is done, and then edges which come into a particular node are all distributed to the various siblings that we get, and we then continue our analysis. So, as if nothing happened. So, eventually this splitting and continuation will take us to a limit flow graph which is a single node, and then suppose we want to retain the original graph with no splitting, that is we want to relate the the gen sets and out sets to the original graph and not with the changed graph. We can simply compute in of B in the original graph, B is in the original graph, as in of B1 meet in of B2 meet in of Bk, where B1 to Bk are all siblings of the split node B. So, this gives us a conservative estimate. So, in the reaching definitions problem this will be a union, in the available expression problem this meet operator will be an intersection. Splitting regions sometimes may be beneficial to optimizations, since data flow information may become a little more precise after splitting. For example, fewer definitions may reach each of the duplicated blocks than that reach the original node. The reason is we do not have as many incoming edges to the each node which has been split. Exactly one incoming edge to each of these split nodes exists, and therefore, we can probably have a little more precise data flow information when we split nodes, but then the penalty we pay is many nodes, explosion in the size of the control flow graph, and finally, the code generated will also be much more than in the previous case. So, that is the end of the lecture on region based analysis and optimizations. Now, we move on to the next lecture on the theory of data flow analysis. So, welcome to the lecture on theoretical foundations of data flow analysis. So, why do we actually explore the theoretical foundations? So, these are the questions that we are going to answer in this lecture. Under what situations is the iterative data flow analysis correct? So far, in the data flow analysis, We just studied the equations, how to implement them in the form of a while loop with a change variable and so on and so forth. But we never thought about the question of is the answer correct, is it always correct or is it correct only a few times, under what situations is the iterative data flow analysis correct. This is a question we never answered. We will try to provide answers to answer to this question. How precise is the solution provided by the iterative algorithm? How close are we to the ideal solution? This is also something that we have never understood. So, let us try understanding this issue as well. Will the algorithm converge? How do we know that we are going to stop? Maybe the iterations will go on and on. So, there is a theory which ensures that the algorithms indeed converge, and we are going to study that theory now. What is the meaning of a solution? So, what do we mean by a solution? Are there other solutions possible, etcetera, need to be answered. So, we are going to define a data flow analysis framework formally, a little more mathematically than we did before, and then the properties of this framework will help us in understanding these questions and answers. Further, by actually proposing a theoretical framework for data flow analysis, reusable components of the data flow analysis algorithm can be identified once once we define such a framework. So, which of these are the components, etcetera, we will see very soon. So, what is a data flow analysis framework? It has a direction of data flow D, there is a domain of values V, there is a meet operator, that is the confluence operator that we have been talking about, and there is a family of transfer functions. So, what are the formal aspects of these? The direction of course is just forward or backward, we are not studying any other type of direction here, and the domain of values V along with the meet operator, they actually form a semi-lattice. So, we are going to study what is a semi-lattice and how is it applicable to our problem. The family of transfer functions V to V, so that is the domain and range are V to V, V and the range is also V, and the family F includes constant transfer functions for entry and exit nodes, it includes identity transfer functions, etcetera. So, we are going to explore these possible topics very soon. So, what exactly is a semi-lattice? So, a semi-lattice is a mathematical structure, an algebraic structure. It consists of a set V and a binary operator meet. So, the inverted V is called as meet. So, that is the one we are talking about. So, why is it a binary operator? Because it takes 2 operands. So, what are the properties to be satisfied by a set and a binary operator in order to become a semi-lattice? So, the set V is closed under the meet operation. In other words, whenever we say V1 meet V2 and we get an element V3. So, if V1 and V2 are in V, then V3 must also be in V. So, this is a well known closure operation and closure property. So, this must be satisfied for the set V and the binary operator meet. Meet is idempotent. So, that is x meet x is equal to x. Okay. So, nothing happens if you apply the meet on yourself. Meet is also commutative. So, x meet y is same as y meet x, and further it is associative. So, x meet y meet z. So, we are associating y and z first and then with x. So, that is, and the answer you get will be the same as when you associate x and y first and then with z. So, idempotency, commutativity and associativity are all true for this set and the binary operator meet. The semi-lattice also has the set V rather has a special element called a top element. So, this is denoted as this T and read as top. So, this is in quotes the highest element in some sense. So, how do you formally state it? For all x in V, top meet x is always x. So, the meet operation with the top always gives you the same element. So, this is the definition of the top element. There can only be one top element. Okay. So, there cannot be more than one in a semi-lattice. So, it may have a bottom element. It is not essential that the bottom element be present. So, this is the inverted T read as bottom. And how do you define the bottom element? For all x in V, bottom meet x is bottom. So, in this case top meet x came down to x, whereas bottom meet x always comes to bottom. So, this is the lowest element, that is why it is called a bottom. So, here is an example. So, we are going to show a semi-lattice in this form of a diagram called the Hasse diagram. D1, D2, D3, D1, D2, D1, D3, D2, D3, D1, D2, D3. So, there are many sets, right. So, here is the empty set and then singleton element sets, 2 element sets and finally, the 3 element set. So, these are actually nothing but the power set of this set D1, D2, D3, this entire thing, the set of all sets of subsets of D1, D2, D3. So, this empty set is the top element and D1, D2, D3 the entire set is the bottom element. The meet operator also defines a partial order less than or equal to on the set V. What is the property of this partial order? X less than or equal to y if and only if x meet y equal to x. So, in other words you want to actually call something less than something else. So, that is why it is called as a partial order and it is defined using the meet operator x less than or equal to y if and only if x meet y equal to x. So, in this case for example, so x less than or equal to y is indicated by the arrow direction y to x. So, this is y, this is x. So, x less than or equal to y. So, the lower elements are all less than or equal to the top element in that some sense. And this less than or equal to is the superset operator. Okay. So, this single element singleton D1 is a superset of the empty set. The D1, D2, D3 the full set is a superset of D1, D2 etc., etc. Any two elements x and y in a semi-lattice have a greatest lower bound GLB. So, what is the definition of G? Such that G equal to x meet y, G less than or equal to x, G less than or equal to y. So, G is lower than either x or y in that sense in the partial order, and if there is any other element z which is less than or equal to z x, then and it is less than or equal to y, then z is also less than or equal to G. So, in some sense the greatest lower bound is not the least lowest element in the set. Okay. So, you really cannot have, if you have any other z which is less than or equal to x and less than or equal to y, then it is also less than or equal to G. So, this is the largest element which is smaller than either x or y, both x and y. So, let us look at the semi-lattice of reaching definitions. So, this is what I showed you here. So, let us formally discuss it now. There are 3 definitions D1, D2 and D3. V is the set of all the subsets of D1, D2, D3. So, I already showed you. So, there are 3 elements. So, 2 to the power 3 is 8. So, we have 8 elements in V. The meet operator is the union operator. So, if you look at D1, D2 and take the meet operation D1 meet D2, then we get the union of the 2 sets D1 and D2, right. So, similarly, D1 and D3 will give you D1, D3 and the meet of D1, D2, D1, D3 gives you D1, D2, D3 and so on and so forth. The diagram shows the partial order relation induced by the meet operator. So, here this is the diagram we are referring to. We do not want to show the transitive relationship explicitly in this diagram. This is called as a Hesse diagram. The transitivity is implicit. For example, D1 is a superset of phi, D1, D3 is a superset of D1. So, D1, D3 is obviously a superset of phi, but this should be inferred by the 2 arcs and there is no explicit arc between phi and D1, D3. So, transitive relationships are not explicit in this diagram, otherwise the diagram becomes too clumsy to understand and read. An arrow y to x indicates x superset y or x less than or equal to y. This is something I already mentioned, x superset y. Each set in the diagram is a data flow value. So, now we are talking. So, we have already seen the iterative data flow analysis algorithm. So, at every point we compute the in and out, they are sets of data flow values, right. So, that set is what we are talking about. So, the data flow value is a set. So, reaching definitions is a semi-lattice and it forms a data flow framework, as we shall soon see. Transitivity is implied in the diagram, I mentioned this already. What is an ascending chain? So, instead of less than or equal to, we just use less than. So, if we use the self element also, then equal to is necessary, otherwise we use distinct elements, then less than is sufficient. So, D1 less than or equal to phi, D1, D3 less than or equal to D1, but since these are all different elements, we can get rid of the equal to and say D1 less than phi, D1, D3 less than D1, D1, D2, D3 less than D1, D3. So, this is an ascending chain. So, this entire thing is an ascending chain and the height of a semi-lattice is the largest number of less than relations in any ascending chain. So, if you look at this 1, 2, 3, there are 3 edges which traverse to the top and the 3 is the height of this particular semi-lattice. Semi-lattices in our data flow frameworks will always be of finite height. We are not going to deal with infinite lattices, infinite height lattices rather, there may be infinite number of elements, as we will see soon. So, we discussed the semi-lattice. So, that was the set V and the meet operator that we talked about. So, in the previous diagram, union is the meet operator and that is the confluence operator of our iterative data flow analysis algorithm as well. So, that is why whenever we take the meet, we get we take the union in the iterative data flow analysis. The data flow analysis framework also had a transfer function set f. So, what are the properties of this set f? F has an identity function I x equal to x for all x in V. So, it does not do anything, takes an element and returns the same element. This is a very important property, f is closed under composition. So, that is if f and g are in the set f, then f dot g, which is the composition of f and g, is also in the set f. So, this is the one which enables us to take one quadruple at a time, look at the transfer function for that quadruple, then compose the two transfer functions and get the transfer function for two quadruples. So, if we do this for all the quadruples in the basic block, we get the transfer function for the entire basic block. So, this is a very important property, and let us again consider the reaching definitions problem. Assume that each quadruple is in a separate basic block, okay. And then we have this equation out b equal to gen b union in b minus kill b, right. So, if you generalize this and call out b as f x, okay, then in b is actually the input that we are going to use. So, that is the x we are talking about. So, b is not the parameter, okay. In b is the parameter and it is modified in this function. So, f x equal to g union x minus k, where g is gen b and k is kill b. So, this is the general form of the equation as a function. So, if you consider two such functions, transfer functions, one for each basic block, which consists of only one quadruple in this case, we have f 1 x is g 1 union x minus k 1 and f 2 x is g 2 union x minus k 2. So, these are the two transfer functions of two basic blocks b 1 and b 2. There is an identity function in the set. So, we easily verified, make g and k, that is gen and kill phi. So, in that case we get f x equal to x, okay, g is phi and k is phi. So, identity function already exists. So, if you consider this as the general form of transfer functions in the reaching definitions case, g and k are of course constants, right. So, this includes an identity function as well. Suppose control flows from B 1 to B 2, there is an arc from B 1 to B 2 in the control flow graph. Then whatever comes to basic block B 2 is the output of the basic block B 1. So, we look at f 2 of f 1 of x. So, f 1 processes the input x and the output is given to f 2 as input. So, that is why f 2 of f 1 of x. So, when we expand this and substitute, we get g 2 union. So, this is our x, which is f 1 x. So, g 1 union x minus k 1 and then minus k 2 as usual for the f 2. So, just rewrite the right hand side. So, you can write g 2 union g 1 minus k 2 union x minus k 1 union k 2. So, we can simply say k is k 1 minus union k 2. So, this part, right. So, and g is g 2 union g 1 minus k 2, that is very easy to see, right. So, g 1 minus k 2. Now, they are constants again, right, k and g are constants computed from k 1 g 1 k 2 g 2. So, if we do this, then this again is of the form f x equal to g union x minus k. So, this is g, this is k. So, this entire f 2 of f 1 of x is of the same form as the original equation, and f 2 of f 1 of x is nothing but the composition of f 2 and f 1. So, f 2 dot f 1, and therefore, composition property is true for the reaching definitions example. The transfer functions of the reaching definitions example are composable. So, let us take an example instead of talking about just mathematical symbols. Here is a simple flow graph B 1, B 2, B 3 and then start and stop as well. There are two definitions in B 1, two definitions in B 2, and then 1 in B 3. This is D 5, that is missed out. So, what are the transfer functions for the various statements? We are looking at one statement at a time, then that is why we have said f of d 1, f of d 2, f d 3, f d 4 and f d 5 instead of basic block. So, the definitions generated by d 1 are d 1 union x minus d 4. Why? D 1 is defining A. So, it kills all statements with A, which are defining A. So, D 4 is a definition for A. So, that will be killed by D 1, that is why the kill function is D 4, kill constant is D 4 k. Similarly, f d 2 is D 2 union x minus D 3. So, D 3 is a definition of B. F d 3 is D 3 union x minus D 2, D 2 is a definition of B, and similarly for D 4, D 4 union x minus D 1, because D 1 is a definition of A. Interestingly, for D 5, we have f d 5 equal to D 5 of course union x minus 5, because there is no definition of C elsewhere in the control flow graph. The transfer functions for start and stop blocks are just identity, they do not do anything. Now, let us compute the transfer functions of the basic blocks and show composition. F d 2 dot f d 1 x is D 2 union D 1 union x minus D 4 minus D 3. So, this the f d 1 part and the outer part is the f d 2 part. So, we get D 1 D 2 union x minus D 3 D 4. Intuitively, this is what we get, it generates D 1 and D 2 and kills all others with A and B. So, that is D 3 D 4. Similarly, f b 2 is D 3 D 4 union x minus D 1 D 2. So, that is exactly the other way, and f b 3 is f d 5, which is D 5 union x, doing nothing else, generates D 5 and then whatever is coming inside passes it out. What exactly is monotonicity of the data flow framework? Unless we understand, this is a very important property, and let us see what it means. So, a data flow framework DFV meet is monotone if for all x y in V and f in the capital F, that is the f is a member of the transfer functions family, x less than or equal to y implies f x less than or equal to f y. In other words, if x is smaller than y, f x is smaller than f y in the lattice theoretic sense. The other possible definition for monotonicity is f of x meet y is f x meet f y. So, both definitions are identical, because the less than or equal to is defined using the meet operator. It will be easy to show that these two are identical. Now, we claim that the reaching definitions lattice is monotone. Let us see how. The meet operator is union here in the reaching definitions framework lattice. So, what we need to prove is that f of x union y, that is here f of x meet y is f of x union y, and this less than or equal to is superset. So, we replace that with superset symbol. F x meet f y is f x union f y. So, now let us expand the f x union y part by substituting the transfer function. So, G union x union y minus k. So, x minus k is the original form. So, instead of x you have x union y. So, x union y minus k. And what about f x union f y, the right hand side? So, f x is g union x minus k, f y is g union y minus k, and therefore, we have g union x minus k union y minus k, and finally, we have g union x union y minus k. So, this is observe same as f of x union y. So, The superset obviously is weaker than equal to. We have proved x union f of x union y equal to f x union f y. So, the superset obviously is trivially true. So, this tells us that the reaching definitions framework is indeed a monotone framework. So, the monotonicity becomes very important for us when we say that the iterative analysis is going to terminate. The next important property of the framework is the distributivity. So, a data flow framework is said to be distributive if for all x, y in V and little f in the transfer function set f, we have x meet y equal to f x meet f y. So, recall that we have already proved f of x union y equal to f x union f y, okay. That is what is needed here. So, trivially we have already proved that the reaching definitions lattice is distributive, we have already done that. But let us prove the other interesting result. If a framework or lattice is distributive, then it is indeed monotone, but if it is just monotone, then it is not necessarily distributive. So, let us say A equal to B, okay. If A equal to B, then A meet B is A, this is obvious. So, A and B are the same. So, A meet B equal to A or A meet B equal to B, both are the same. Let us take A meet B equal to A. So, by the definition of the partial order relation less than or equal to, if A meet B equal to A, then A less than or equal to B. So, this is the definition of equal this less than or equal to. So, now apply the definition of distributivity. We know that we must have x meet y, f of x meet y equal to f x meet f y. So, these two are now going to be substituted for A and B, because A equal to B is needed and we have f x meet y equal to f x meet f y. So, this is A, this is B. So, we substitute in this particular relation A less than or equal to B. So, we get f of x meet y less than or equal to f x meet f y. This is exactly the definition of monotonicity. So, distributivity indeed implies monotonicity, but monotonicity does not imply distributivity trivially, because this is less than or equal to, whereas equal to is a stronger relation. So, it is easy to construct a counter example to show that a lattice which is monotone need not be distributive. So, we will see one very soon in the constant propagation framework later. So, we have proved that the reaching definitions lattice is also distributive, it is monotone and it is distributive. Now, let us take a look at the iterative algorithm for data flow analysis, assuming that there is a forward flow. Out of B1 is some initial value, and for each basic block B not equal to B1, we have out B equal to top. So, remember the lattice of reaching definitions, top is phi, okay, nothing. So, this is a DFF data algorithm for forward flow. So, we do not use any reaching definition confluence operator here, we use the generic meet operator here. That is why the generic top value has been used, not phi. The change part remains while changes to any out occur do. For each basic block B not equal to B1 do. So, we go on iterating until the out or in sets are changing, or rather do not change anymore. So, in B is meet of out P, where P is a predecessor of B. So, we had union here in the reaching definitions case, intersection in the available expressions case. So, the generic operator is meet. out B, now you apply the transfer function f b on in B. So, remember it was G minus G union x minus kill, right, x minus k. So, that is the transfer function we are applying on the set in of B. So, let us take the same example and continue it. We have the transfer functions from our previous example, f b 1 equal to d 1 d 2 d 1 comma d 2 union x minus d 3 comma d 4, similarly f b 2 and f b 3. Here are the two equations. So, this iterative algorithm requires 3 iterations to converge. So, in every iteration we use the depth first search order. So, we start here, go here, then here, sorry, we go here, then this and then this. Okay. So, when we come to this, both these results are available to us for the meet operation, otherwise we need to make one more iteration. So, if we do that, apply these things. So, in of B 1 equal to in of B 2 equal to phi, that is well known, nothing is coming from the start block. Out of B 1 is d 1 comma d 2, that is very simple to see. So, these are the only two definitions which come out, and that is what we get that by f b of in B. So, in B is phi. So, if you apply f of B 1, then you get x minus phi, this is actually in B is phi. So, this becomes phi minus d 3 d 4, nothing. So, that is phi again. So, this part is d 1 comma d 2, that is what is mentioned here. It is very similar, out B 2 is similar, in B 2 is phi. So, we apply x as phi here. So, we get d 3 d 4. What about in B 3? We need to take the min of rather meet of these two, that is the union. So, out B 1 union out B 2, which is d 1 d 2 d 3 d 4. Okay. So, these two are d 1 d 2, this is d 3 d 4. So, we get d 1 d 2 d 3 d 4. What about out of B 3? So, we now apply this transfer function d phi union x. So, that is d phi union in of B 3, that is the x, the parameter coming in. So, we get d 1 d 2 d 3 d 4 d 5. So, this is intuitively also correct, because whatever comes here and what is generated here will all be available, will all reach this point. So, this point all the 5 definitions reach, that is why the reaching definition set contains all these here. What are the properties of the iterative data flow analysis algorithm? So, we have defined many terms now, monotonicity, distributivity, composition of transfer functions and so on and so forth. Let us see where some of these actually fit. If the iterative algorithm converges, the result is a solution to the data flow equations. So, we are not saying it converges, we will see that a little later. If it converges, then the result is a solution to the data flow equations. So, this is obvious because we iterate. See, if the equations are not satisfied by the time the loop ends, at least one of the outsets change and then we iterate again. So, if they were not satisfied, then we would have iterated again and again, So, the constraints that we have set should have been satisfied. So, only then the outsets or insets do not change from one iteration to another, and that is the time we stop. If it does not change once, it does not change again in any of the other iterations as well. If the framework is monotone, then the solution found is the maximum fixed point of the data flow equations. So, maximum fit point is a property such that in any other solution, values of in B and out B are less than or equal to the corresponding values of the MFP. So, this is the maximum solution. So, any other solution is actually going to be just weaker. Okay. So, this property can be proved by induction. So, we can show by induction that the values of in B and out B only decrease in the sense of the less than or equal to relation. So, in other words, we start from the top of the lattice, that is phi, and then we actually move downwards. So, when we move downwards, we get weaker and weaker solutions in this less than or equal to sense. So, now if the framework is monotone and is of finite height, then the algorithm is guaranteed to converge. This is obvious almost, because we initialize the values to phi, and then with each one of the iterations we can only move downwards. How how many steps can we go down? That is nothing but the height of the lattice. So, the data flow values decrease with each iteration, that is we go down the lattice. The maximum number of iterations is the height of the lattice into the number of nodes in the flow graph. We are not assuming that the depth first search numbering is used here. So, in the worst case, just an upper bound, height of the lattice into the number of nodes in the flow graph is the maximum number of iterations possible. You cannot really do anything more than that, because for each one of these nodes, the stabilization occurs, let us say, in one iteration. So, in to get this stabilization, we need to pass through the entire lattice. So, from phi to the last one. So, that is the height of the lattice, and for each node we have to do it as many times. So, this is the product. So, now we want to look at the meaning of an ideal data flow solution. So far when we computed data flow values and solved the equations in the iterative way, we always said the values are conservative, they are not the best that we can get, but practical situations force us to accept these conservative values and so on. So, that makes it interesting to see what exactly is an ideal solution. So, to find the ideal solution is very simple. Find all the possible execution paths from the start node to the beginning of the basic block B. So, you are really now looking at the execution paths. Okay. So, some conditions may be true, some may be false during execution. So, we are looking at the path really during execution. Assuming forward flow, compute the data flow values at the end of each path using composition of transfer functions, and apply the meet operator to these values to find their greatest lower bound GLB. So, you have many paths coming to that basic block. Let us say the input of the basic block. Now, at the input, for each path apply the composition of the various transfer functions of the basic blocks that occur along that path and find the value. Now, there are many paths, so you take the GLB. So, ideal B is the meet of FP V in it, this is the initial value. Now, what is P? P a possible execution path from start node to B. So, no execution of the program can produce a smaller value for that program point, that is the input of B in this case, because we have considered all the execution paths. So, there is nothing else that can be possible. So, if we had considered one of the execution paths, then maybe the other one would have produced a smaller value, but now we have looked at all execution paths and then found the values, taken their meet. Any answer which is greater in the sense of less than or equal to this partial order than this ideal value are incorrect. One or more execution paths have been ignored in this case. So, maybe the meet did not give us take us slow downwards sufficiently. Any value smaller than or equal to the ideal is conservative. So, that is safe. So, one or more infeasible paths have been included in this case. So, this is what happens when we do iterative analysis. Closer the value is to ideal, more precise it is. So, this is the best that we can get, and we still have not seen where we stand in the case of the iterative analysis. So, we will understand the meaning of the values produced by iterative analysis which are practical algorithms in the next lecture. Thank you.